Okay, basically this is the part that we missed to record last time, so I'm going to talk about it a little bit. So you have basically the recorded version. So this is the continuation of our talk about digital transmission fundamentals. So we talked last time about, for example, why we use digital transmission. We talk about line coding. We talk about Manchester coding. So today we're going to talk, continue talking about modulation and demodulations. So first, we're going to talk about capacity. That's how basically how you can determine how many bits per second a given channel can basically carry. By channel here, we mean the channel can be anything. If you consider, for example, copper wire, it can be our Ethernet cable, or it can be our, if you're transmitting Wi-Fi, it can be the air as a channel, as our medium. So the capacity that we define is defined by the Shannon limits, and it's named after Claude Shannon, who basically established this limit, these equations. So it's equals, channel capacity is equal to B, which is stands for bandwidth, multiple log 2 of 1 plus signal over noise. You remember we talked about signal to noise ratio? Basically what it means is like how strong is the signals comparing to the noise that we have in our channel. You remember we mentioned that you can reduce the noise, but it never gets to the zero. But what we can do is we can reduce. So in order to have the higher channel capacity, basically we need to have stronger signals, which means louder signals, stronger signals, or lower noise. By lowering the noise, we can have higher channel capacity. By increasing the strength of the signal, we can have higher, basically, signal to noise ratio. So basically what it means is a higher capacity. But the bandwidth is somehow is limited by the basically which frequency we use, which channel we use. It's sort of limited. So what we can do is working with signal to noise ratio. So this is basically a limit that we cannot basically surpass this. We cannot go beyond this. What we can do is, the best is to getting close to this limit. So if we get close to this limit, we are doing basically a very good job, but as this is a theoretical limit, we cannot really bypass that. So when we talk about signals, usually we are talking about, when we're talking about basically capacity of a channel, we are talking about the bandwidth and the signal to noise ratio. The way to talk about this is, one way is in terms of basically analog signal. So you can think of sinusoid signals. And we are talking about sinusoid waves. Here's a simple one you can see. So when we're talking about these sinusoid waves, there are a couple of properties that we need to consider. One is like, for example, the amplitude of the signal, which means how strong is the signals. How loud is the signal? You can consider it as a loudness or as the strength of the signals. Another one is basically, another property is the wavelength of signals. So for example, how long is the wavelength? So if you consider the speed of light, for example, considering the signal propagate equal with the speed of light is basically 300 million meters per second, or we can say 30 centimeters per nanosecond. So if I have a wavelength of 30 centimeters, so it means in each second I can have basically 1 billion wavelengths. So that 1 billion wavelengths can be translated to 1 gigahertz channel. 1 gigahertz channel, we have 1 billion wavelengths, 1 billion basically signals per second. So that can be basically using this as a rule of thumb, considering what's the wavelength and how to calculate it. So if you consider the modern Wi-Fi, we're using 2.4 gigahertz or 5 gigahertz in our daily, basically, when we're using Wi-Fi. So considering 2.4 gigahertz, it can be around somewhere 12.5 centimeters per the wavelength of the signal, or for 5 gigahertz, the wavelength can be 6 centimeters. But it turned out that we send signals, you don't really use a single frequency. We actually use a range of frequency, as you know. For example, if you remember when, most probably you have seen when we were talking about Wi-Fi, we were talking about certain channels, for example, channel 1, 6, 11, each one has like 20 megahertz of bandwidth. So we are using a certain number of channels, a certain range of frequency in order to transmit our message. So given that we are using waves, there's a whole bunch of ways we can represent bits. For example, here you can see two different examples, amplitude shifting and frequency shifting. So what it means, the amplitude shifting basically is one of the simplest way we can represent bits. So what it means, we can change the amplitude of the signals in order to represent different bits. For example, here in this example that you can see here in this sinusoid wave, we can see in order to transmit one, as a bit 1, we can go high amplitude. For transmitting 0, we can go lower amplitude. So by changing between higher and lower amplitude, we can send 1 and stream bits of 1 and 0. So I go high amplitude, high. So it means like 1, 1, 1, 1. Then I go low, low, low. It will be 0, 0, and so on and so forth. For frequency shifting, it's work different. Frequency shifting, basically what will vary is the frequency of the signal, not the amplitude. So in order to, for example, represent 1, we're going to, for example, have a low frequency signals. And in order to transmit, for example, 0, we double the frequency of the signals in order to represent 0. So by changing the frequency of signals from two different, for example, frequency, let's say, for example, this is 1 gigahertz, this is 2 gigahertz, just an example. So we can represent basically 1 and zeros, okay? So basically that's a frequency shifting. Here we are changing the amplitude. For ASK or FSK, we are changing the frequency of the signals in order to represent our information. So talking about amplitude shifting, it turns out to be very basically simple, and it's very commonly used, especially in wired network. And the reason is that when you have a wire, your medium is controlled. So if you put a signal on one end of the wire, you're going to basically, it's not going to decrease a lot on the other side, because the resistance of the wire is very, very low. That's the whole idea of transmitting basically our power using wires, because they have very low resistance. So amplitude shifting is commonly used in wired system, just because it's very simple and it works great. So most common wired Ethernet today use amplitude shifting. For example, 100 base T, 100 base T, and 1000 base T that are representing 100 megabit per second and gigabit per second Ethernet are using something called PAM5. What it means, PAM5, is we have 5 different level of amplitude modulations. Imagine, so what it means here, we have 5 different level of amplitude. We're sending 5 different levels of, basically we are shifting between 5 different levels of amplitude in order to transmit our information. So as you can notice here, we are sending, with each basically pulse signals, we can transmit 2 bits, because we have 5 different options, we can represent 2 bits. So they're called pulses because you're sending pulses at this different amplitude. So think of this basically is you are, for example, changing the voltage, okay? Because we mentioned that amplitude is the power of your signal, so we are changing the voltage from -2 all the way to 2 in 5 different levels. So for 10G base T Ethernet, which is 10 gigabit Ethernet, is more relatively recent standard for Ethernet. We are using a PAM16, which means 16 level of basically amplitude modulation. So it means we are changing the voltage in 15 steps, 15 level. So it means we can basically represent 4 bits per pulse. So another forms of modulation that is very popular is what we call it phase shifting. So here, unlike amplitude shifting, where we are adjusting amplitude of the wave, or frequency shifting, where we were basically using different frequencies, the phase shifting, we change the phase of the signals in order to represent different bits, 0 or 1. For example, here you can see this signal, let's say start from 0. The phase of the signal, let's say it's 0. So by going this phase, we are representing 0 to basically send this bit as 1. We shift the phase of the signal by 180 degree, as you can see here. These two signals have 180 degree different phase. So we should change the phase to represent different bits. So phase shifting is very useful when your channel or your medium is such that you can have significant variation in signal strength. So unlike the wire, for example, when we are transmitting signals over the air medium, it's not a controlled environment, so really amplitude shifting is not going to help us. We need different type of modulation. So we usually use phase shifting in order, for example, in our wireless systems. So here you can see two different examples of it. We have binary phase shifting or quadrature phase shifting. In binary phase shifting, we have two different phases, as the name says, it's binary. We have either phase 0 or phase pi, or it means 0 or 180 degree. It used in basically 802.11b, the older Wi-Fi standard, at the lowest speed of 1 megabit and 2 megabit per second. Then there's also this quadrature phase shifting, where we are using 4 different phases. For example, 0 pi over 2 pi and 3 pi over 2 for representing 0, 90, 180, and 270. So here we have 4 phases. As you can see, we are using 4 phases, and here we are using just 1 phases. And it turns that this QPSK modulation used in also the whole Wi-Fi standard 802.11b, but in a higher speed, 5.5 megabits and 11 megabit per second Wi-Fi standard. So why we use basically phase shift keying or PSK is basically that it turned out to be very easy basically to change shift phase of the signals. For example, you can look at these 3 signals here. Let's say we have this signal which represented by the green, and this signal that is representing by the blue. So you can see that this basically these 2 signals have like a pi over 2 different phase. This between this green one and the blue one. But if we combine these 2 signals, we get this the middle signals, okay, which has pi over 4, the phase of pi over 4. So by combining different signals, we can generate various signals with various different phases. So that's why it's very popular using phase shifting modulation, PSK modulation. So The fact that's exactly how hardware does it using something like IQ modulations. So I is in phase component, as you can see in this phasor diagram. They call it phasor diagram. I is the in phase component. Q is a quadrature component. I is basically 0 degree. Q is minus 90 or 90 degree. A symbol is a nonlinear combination of I and Q. So if you consider this amplitude, this represents the amplitude, the length of this, let's say, arrow represent amplitude, the angle represent our phase, okay? So let's say, for example, for binary phase king that we mentioned that we have two different phases for binary phase shift king for BPSK. We have phase 0 and phase 180. So you remember we mentioned this is our phase. The phase is the angle here. This is the phase that we have. So considering this, the IQ modulation would be, if the phase is 0, basically means sitting right here. If the phase is 0, it means I is 1 and then Q value is 0. Bad writing. And for the 180 degree, which means this signal, then the I would be -1 and the Q would be still 0. But talking about the quadrature phase shift keying, then we have 4 phases. We have 0, we have 90, we have let me see if I can change the color here. So here for QPSK we have this signal 0, we have this 90 degree, we have this 180, and we have this 270, 2 pi over 2. So for 0 degree is you can see the I value is again 1, Q value is 0. For 90 we have I value which is 0, the Q value is 1. For 180 degree I value is -1 because this is the I value, this one for 180. The I value is -1, Q is 0. It look like a heart. Q is 0, and for the 270 or 2 pi over 2, the Q is I is 0 because I is sitting right here, and Q is -1. So that's the IQ modulation. For you see, we already talked about BPSK, binary phase keying, as shift quadrature phase shift keying. Then what's really available, and the reason why we are using, we are going into this all these IQ things. IQ constellation is the way to basically show easily or with a visual representation what's really happening in the physical layer. And so the way to think of it is it's like is if we take these IQ values and we represent them in a 2D grid. Let's like what you see here, like what you see in this, for example, and we can call this basically the same IQ constellation. For example, for on-off keying, what it means basically having some voltage or having 0 voltage onning and offing, in order to represent basically 0 and 1s. You can see here for on-off keying, if you are having 2 different amplitude, one is basically this amplitude here, and another one is 0 or off. So you can see the phase is not changing because the phase, you remember the phase was the angle of this, but here the angle is 0. The phase is same for both, and the Q value is 0. For ASK was amplitude shift keying. We're changing the amplitude between the two signals. We have this signals has a higher amplitude, the other one is a lower amplitude, but we are not doing anything with the phase of the signals. With BPSK or binary phase shift keying, you remember we're not changing the amplitude, we are just changing the phase of the signals. So you can see the amplitude of these two signals are equal, because you remember this is the length of this is the amplitude. This length is equal with this length. Okay. So the amplitude, the power of the signal or the amplitude is the same, but what is changing basically is the phase. This is having the zero phase, and this green one having like pi. The phase of it is a pi, 180 degree. And if for quadrature phase shift keying, we have the same thing. We have basically same amplitude. As you can see, the length of, let's say, if you draw this arrow, the length of all these four arrows are equal. But what is changing for each signal is different phase. For example, this signal has basically pi over 4. The phase is pi over 4. This is basically it can be basically 90 and another 45 here, 135. This is another. So you can see here we are changing basically. If you consider this arrow, we are changing the phase of each one of these signals. The amplitude is same. We are just changing the phase of the signal. So you can see it's very easy to represent basically what's happening in using basically 2D plot. It makes it very how to say, easy to understand what's happening. So now at some point at the link layer, we have bits. Bits are coming in from, let's say, network layer. Talking about like symbol versus bits, we have some packets from the network layer, and we have, imagine we have packet from network layer. We have some frame at the link layer with some bits in it, 00, 1, 1, 0, 1, 0, organized into bytes, into octets. But down in the physical layer, we can't necessarily transmit the whole byte. It might be that we can only transmit a couple of bits at a time. And so in the physical layer, we talk about symbols. And a symbol is the unit of transfer that the physical layer can provide. So, for example, for BPSK, binary phase shift keying, for this one, we have 1 bit per symbol. You remember we had 2 different phases, phase 0 or basically, no, this is not showing the phase, but for binary phase key, we have 0 or pi. So we can basically represent 1 bit per symbol, either 0 or 1. But for quadrature phase shift keying, we had 4 different phases. So we could represent 2 bits per symbols. So for example, 0, 0, 0, 1, 1, 0, and 1, 1. So each symbol that we transfer, we can transmit 2 bits. So for 100 base T Ethernet, that we use basically in 100 megabits per second in Ethernet using Cat5 cable, we have 5 different voltage for PAM5, -2, -1, 0, +1, and +2. So basically, it's not a bit; it's a slightly more, slightly more than a 2 bit per symbol. So talking about that, now finally we can talk about amplitude. We already talked about amplitude shifting. We talked about phase shifting. There's this thing called the QAM. It's very, very common. You see it in almost all modern communication systems. It's called QAM, which really stands for quadrature amplitude modulations. Or basically, this means phase and amplitude at the same time. We're changing shifting the phase and amplitude of the signals at the same time. And so, whereas for amplitude shifting, we only change the power of the signals. For phase shifting, we only shift the phase. For QAM, we basically change both. We have, let's say, we have different modulation in the QAM. We have 16 QAM, 64 QAM, 256 QAM. 16 QAM represent like 16 symbols, 4 bits per symbol. For 64 QAM, it's 64 different symbols, which we can represent 8 bits per symbols. And for 256 QAM, we have 256 different symbols that we can represent. Each symbols can transmit basically 16 bits per symbol. So it's maybe a little bit more clear here using this how to say, IQ modulation in 2D, representing in 2D. Here's basically 16 QAM. We represent 16 QAM. These bits here that you can see are basically the bit that we're transmitting. This number in gray is representing IQ value for this particular signal. So as you can see here, if you consider, for example, if you compare, let's say, this signal, the blue one that I draw with, let's say, with this green signal that I'm saying, these are two different signals. You can see the length of the these two arrows are different. This has definitely higher amplitude. This has a lower amplitude. So this is having this particular phase. So for example, for the green one, the phase is this much, okay? You remember this was the phase. For the blue one, this is the phase, right? So you can see for blue one, we have different phase, different amplitude. For the green one, for this one, basically, this we are comparing this and this. So with this and this, we are having different amplitude and different phase. So if I want, for example, represent a value, for example, 1, 0, 1, 1, 1, I don't know, 0, 1, 0, then I can basically break it because each symbol can be 4 bits. So this basically means this one, this part means this one, right? So here, if I want to transmit these bits, I'm going to transmit my signal with this amplitude and with this phase, okay, from here basically to here. And if I want to transmit this set of bits, I go with this amplitude and this phase. So you can see you're changing basically both amplitude and the phase of the signal. So we can have basically each symbols that we send in physical layer can transmit basically 4 bits of information. So if this gives, you can see it's showing basically different level of amplitude. Let's say this is the power, we're going to 25, 75% of the power, and we're changing the phase, different angle of the phase in order to represent different information. So in today's network, we have different, basically, let's say we're using different modulations. You remember we mentioned ASK and on-off keying or amplitude shift keying and on-off keying. It's used in wired Ethernet. FSK or frequency shift keying, it doesn't use, we are not using it anymore really in modern wireless systems. But as an example, maybe national weather station radio can use this basically frequency shift keying or Bluetooth, all the standards. For binary phase shift keying, as we mentioned, we use in 802.11b, like an old Wi-Fi standard, or WiMAX. For quadrature phase shift keying, we use in a Wi-Fi standard, or in some example in the Zigbee standard. It's a low power, short range wireless standard. For example, 16 QAM can be used in 3G, or some people call it 3.5G, or 3G updated standard, or WiMAX, and like 16 QAM are more popular, basically are used in LTE network, and also 256 that used in modern wireless or Wi-Fi standard. So you can see by going up, basically remember each basically pulse could represent more number of bits. For example, here we could represent, each pulse could represent 1 bit. Here each represent 2 bits. Here each pulse represent 4 bits, represent 8 bits, basically a whole byte. You can send a whole byte of information with 1 pulse. Here it represents like 16 or 2 byte information. So we saw that we are basically many ways to represent bits in terms of analog signal. We can change frequency, we can change amplitude, we can change phase as well. Wired Ethernet use amplitude shifting. We mentioned that amplitude shifting is useful for when we are having a controlled medium like a wire, and wire has a very low resistance. Most technologies nowadays use phase shifting or phase and amplitude, which is QAM. You remember in QAM, we said we are changing both phase and the amplitude of the signals. So we could represent QAM symbols as a linear combination of in-phase component or I and quadrature components Q, or what we call it IQ modulations. So that's basically how it's happened in the actual basically hardware. And you could see how easy is using this 2D plot using Pacer diagram to understand what's happening in the physical layer. But let's continue talking about errors and coding, and a way to introduce some redundancy of the data is that you can protect yourself against bit errors. You remember we mentioned earlier that we need basically coding means like adding some redundancy in our information in order to make sure that basically the data arrives in the destination correctly and can be read correctly. So recall that the channel limit, the capacity of the communication channel is determined by the bandwidth and then base 2 log of 1 plus signal to noise ratio. And so basically, this means is that in practice, the possible data rate is bounded by these signals, the signal to noise ratio. So if your signal is stronger, you can send data faster. If the noise in your circuit is lower, you can send data faster, of course. So the importance is that this is a theoretical limit, as I mentioned. In fact, your system today can get close to this theoretical limit. This is if you notice, like when you have a higher number of bars in your cellular network, when you see that your antenna of the cellular, when there are higher bars there, you can send the information faster because basically that means your signal to noise ratio is high. So the noise is low or your signal is strong, you're closer to maybe the tower, so you can send information faster because the signal is stronger. So because there is noise in the system, we mentioned that you can reduce the noise, but you cannot really eliminate it. So because there is a noise on the receiver, just in the hardware, what we receive is closer to this. For example, considering quadrature phase shifting, that we have 4 different phases. If you consider this, basically what we show was like, okay, we put 1 point here like this, 1 was here, 1 was here, and 1 was here. Okay, but when you read the amplitudes or phase of signals, it doesn't really fall here because of the noise. Your basically the phase of this signal that you receive might be slightly different. For example, the signal might fall here, fall here, fall here, okay, or fall here. The amplitude might get reduced through the noise or different reasons. So what you can receive might be like this type of signals that you with different amplitude and the phase. But in this particular example, because the difference basically between amplitude and the phase of the signal that you can read is very large. So basically, whatever you read in these boundaries, you can consider it like this particular basically information, or like 0, 0. So the error doesn't cause too much. Like this is 0, 0. This is 0 and 0. Signal doesn't cause too much problem. But consider a denser modulations.